myself Dr. Sangeeta Sharma, Associate Professor PG Department of Chemistry, Government डूंगर कॉलेज बीकानेर। आज हम MSc प्रीवियस पेपर थर्ड में सरफेस केमिस्ट्री के अंतर्गत माइक्रो इमल्शन के बारे में पढ़ेंगे। माइक्रो इमल्शन से पहले हमको इमल्शन के बारे में जानना जरूरी है। Emulsion is a colloidal system in which the dispersed phase and the dispersion medium both are immiscible liquids. For example, milk is an emulsion in which particles of a liquid fat are distributed in water. There are two types of emulsion: oil in water. In this type, oil particles dispersed phase are distributed in water dispersion medium. For example, milk, vanishing cream, etc. It is designated by O/W or O-in-W. The second is water in oil type. In this type, water is the dispersed phase and its particles are distributed in oil which act as a dispersion medium. For example, butter. It is designated by W/O or W-in-O. The two types of emulsion can be experimentally identified in a number of ways, such as indicator method, dilution method, conductivity method, fluorescence method, and filter paper method. Microemulsion or micellar emulsions. This term is coined in 1958 to describe colloidal system. The term microemulsion was applied to systems obtained by emulsifying an oil in aqueous surfactant and then add co-surfactant, which is generally an alcohol of intermediate chain length. Benzene, hexanol, potassium olate, water, etc. might be the component of a typical microemulsion. The usual milky emulsion becomes transparent when alcohol is added to it. Techniques like light scattering, etc. have shown that the resulting system consists of either oil in water or water in oil emulsion with particles having diameter in the range 10 to 100 nanometer. It is seen that whether the oil or water is continuous, the degree of uptake of the other component may be quite large. The difference between emulsion and microemulsion are: microemulsion consists of particle size 10 to 60 nanometer, at least an order of magnitude smaller than those in porous emulsion. Second, the microemulsion are formed spontaneously, while porous emulsion require vigorous stirring. Third, microemulsion are stable with respect to separation into their component, while porous emulsions may have a degree of kinetic stability but finally separated. Fourth, microemulsions are isotropic and optically transparent, while porous emulsions are cloudy. The arbitrary formation of microemulsion delta G is less than 0 is associated either with presence of a negative interface tension due to higher pressure in the film formed by the mixture of the surfactant and the addition at water oil interface or with entropy contribution, and also or the energy repulsion of the electric double layer. The porous emulsion are thermodynamically unstable system whose kinetic stability is determined by the force of repulsion of the electrical double layer or the surface of the globules and the van der Waals force of attraction. The thermodynamic stability of microemulsion is determined by the free energy of double layer formation, the entropy effect of, and by force of electrical double layer. The van der Waals force of attraction play a secondary role, so they regard as a swollen micelles. Emulsion means the presence of two phases with an interfacial free energy associated with the phase boundary. Their small size make the specific area large for microemulsion with a large free energy contribution from surface tension. The mixed film of surfactant and co-surfactant make the interfacial free energy negative. The increase in overall free energy with decreasing particle size may be offset by a favorable and thus a negative T delta S term is in which delta S describe the entropy of mixing the microemulsion particles with molecules of the dispersion medium. As the number of microemulsion particles increases with decreasing particle size, the value of delta S becomes more favorable with decreasing. Microemulsion is complicated example of micellar solubilization. There is no problem with spontaneous formation or stability with respect to separation. Ordinary and reverse micelles provide the basis for both oil in water and water in oil microemulsion. The phase diagram for the four-component system rather than surface tension that holds the key to understand the concept of microemulsion. The small shade circle on the extreme left show a micelles with little or no solubilization. If we move from left to right, the particles increases in size due to increasing solubilization. The circle on the extreme right shows an emulsion particles, that is an oil drop with a monolayer of surfactant on the surface. An exactly continuum of states as shown in figure 1 is not physically achieved because most emulsions are prepared by condensation. But microemulsion also exists between the two extremes. The phase diagram are an effective way of representing the complex behavior of surfactants system. Phase diagram of microemulsions shows that non-ionic surfactant form microemulsion at definite temperature in the presence of co-surfactants. These have simple phase diagram having three components are present. Figure 2 is a composite of both experimental and schematic interpretation portion. The rectangle diagram exhibits the experimental behavior of the system. Water, cyclohexane, polyoxyethylene -8,6 nonyl ether. All the system studied were found to contain 5% surfactant with a varying amount of cyclohexane and water. Temperature was the experimental variable, and hence as it was changed, the nature of the phase present was recorded. The presence of different equilibrium phase is shown by different area on the rectangular. The latter is divided diagonally by a pair of lines that trace a ribbon-like pattern. This pair of lines cross twice, and so ribbon is divided into this region. These regions, along with the regions above and below the ribbon, define 5 different phase situations seen at different temperature and composition. The ternary phase diagram that have been superimposed on the experimental plot in figure 2 shows 5 different areas on the rectangular diagram. The staked triangle represent the oil-water surfactant, which is as phase diagram at different constant temperature. Since the experimental data were obtained 5% surfactant, the rectangular plot slices through the triangles 5% of the distance towards S from the oil-water base of the triangles. As the micellar phase changes from water continuous to oil, continuous with the increased temperature, it is a difficult situation to describe the micelles in the three-phase area that exist at the intermediate temperature. The homogeneous micellar phase constitutes the microemulsion. For 5% surfactant system, it is only over a relatively narrow range of temperature that it is possible to have fairly extensive solubilization of either oil or water in the micellar solution. A 4-component phase diagram P and T constant is to use a trigonal prism in which one of the component rather than T changes along the rectangular face. Figure 3a is a partial phase diagram for the system water benzene potassium olate pentanol. The homogeneous micellar solution are shown by unshaded area in the individual triangles. These micellar systems are equivalent to the homogeneous area in the ternary phase diagram, figure 2. At equilibrium, up to 50 weight% of benzene can be incorporated into the system with only minor changes in the maximum water uptake. The resulting 4-component microemulsions is the same as that obtained by emulsifying the oil and water with potassium olate and then adding pentanol. This is true for equilibrium phase diagram. The diagram tells nothing about the rate at which the equilibrium is obtained. Figure 3b show the same as in figure 3a, replotted with the variables interchanged. This shows how the homogeneous area expands in the size with increasing potassium olate concentration up to 0.44 mole per kg. The homogeneous area shrink with higher concentration as other surfactant phases compete for the components. Now we take application of microemulsion. Systems in which one liquid phase is finally dispersed in another under the stabilizing effect of one or more additional component find application in a wide areas: shaving lotion, floor wax, cold creams, beverages, concentrates, and pharmaceutical products are a few examples. Recent research in this area has been done to solve the problem of tertiary oil recovery. Microemulsion has been used in synthesis of certain polymers in emulsion polymerization. Emulsion drops are the site of the polymerization and have commercial importance. Emulsion polymerization is applicable only to relatively insoluble in water monomers like styrene. A porous emulsion of monomers in aqueous surfactant is prepared with a water-soluble indicator. For example, hydrogen peroxide in solution. The surfactant concentration is above CMC, that is critical micellar concentration, so surfactant molecules are present as monomers, micelles and emulsifier at the oil-water interface. Therefore, the monomer is present in porous emulsion drops solubilized in micelles as dissolved molecules in water.